So this is this basic problem. So now we're going to apply it to the real world. What you might do in your life is a medical example. Okay. Let's see. Oh, no, the opposite of that is why you need a catheter. You can't urinate. I had that medical point backwards. I apologize for that. Okay, so now we're going to do real-world numbers here, and we're going to learn something. Maybe. I mean, let's not get too ambitious here. Okay, so we're going to do an IV transfusion here. All right. So you can see how some of these just letters here turn into real things. IV transfusion. And I have some pictures to help illustrate the point. They're all completely important and critical to the lecture. Here we go. Okay, so say you're a candy striper, which I did check was an okay thing to say. So you're a candy striper. And you've got a 1 liter IV bag here like this. Right? 1 liter of whatever they're going to put in. Blood, say. Rho is 1020 kilograms per meter cubed is the density of the solution. I guarantee if the density is marked on the bag, it is not in kilograms per meter cubed. So you'd have to convert that. Okay? And the mean orderly says to transfuse in 8 hours. Right? They want this 1 liter to go in 8 hours. And the question is how high to place the bag. So this is why all candy stripers must have a degree in physics if they're going to be able to do this. And you know you have to place it high, right? So anytime you see somebody with one of these bags, it's like way above their head. Right? Why is it above their head? Is it to keep little kids from coming in and putting stuff in the bag? No. Because they're using gravity to shove it into your arm. So you think physics doesn't matter? Every patient in the hospital is using potential gravitational potential energy to infuse. You would think, wouldn't they use a pump? No. We're not spending money on health care. We're using gravity. It's just a rod in a bag. I mean, give me a break, right? So let's see. So then what happens is, it's always the case that the person's down here. None of this is, to scale. And it's going into their arm. And if we zoom in on the arm, you'd have to take a few things into consideration in this calculation. Is the thing going into the arm is called a catheter. Okay? If you watch a lot of CNN, like I do recently, you would think that catheters are only put into your private parts, right? That's what all the commercials are about catheters. But any flexible thing that goes in your body is a catheter. Okay? So when you get an IV, that thing is also a catheter. It's not just things to let you fly your airplane longer. Okay? So the catheter has a radius, sort of the small radius, of 0.3 millimeters. You want it to be small, right? Because it's inside the needle. It has to be small enough to go in the needle, and the needle goes in your arm, and somehow they remove the needle, and the little tubing stays in your vein. And then here's something else, is the pressure in your vein is not atmospheric pressure. It's higher than that. Remember, so when you're checking your blood pressure, it's 120/80, but this is a vein coming back, so it's a little lower. So let's say that the pressure here is 50 milligrams of mercury, because that's what they're going to say, millimeters of mercury here. So you got to flow into a region where it's 50 millimeters of mercury. And you got a bag and yada, yada, yada. Okay? So the question is, could you do this? Right? Could you set up this situation? Let's see. I found this example. I'm not sure what's going on here. I think this is Halloween related. This will be on the exam. It's 2 sources, and it's going into someone's mouth, and yeah. But here, let's get back to a real example. See here, it's way up in the air. How high does this disorderly have to adjust it here to get it in there? Orderly. There's an 80s movie called The Disorderlies, which I highly recommend. It's the Fat Boys rap group. Highly recommend. So what you got to do is, most of the numbers you need here were sort of given to you, pressures, radii, but you got to deal with this medical part. We want to transfuse 1 liter in 8 hours. What does that mean? Okay, so we didn't talk too much. We talked a little bit about flow rates. Oh my God, Q equals what? The flow rate is clearly, it's 1 liter in 8 hours, right? So that's 10 to the minus 3 meters cubed in 8 times 3,600 seconds. Right? So now you have a flow rate of 3.5 times 10 to the minus 8 meters cubed per second. So you converted it to MKS. So you tell the doctor, hey, I converted this to MKS. And they're like, okay. If we could pay you less, we would. And then you got to know what to do with the flow rate. I think I briefly said this last time, but anywhere you are in a flow, the flow rate is basically what's happening here with AV and AV. Right? You have to conserve the flow rate because you have to conserve the amount of liquid. So it's really just AV. So V2A. Or now let's see, did we call the high one 1 last time? Which one was 1? Yeah, okay, let's call it V1A. Screw up my notes. There we go. So we're going to call the bag area V1, up in the bag. Right, and then you say it's equal to V1 times pi. Oh, no, I'm sorry. We're doing this down at the bottom, too. Sorry. We're calculating the flow rate here. Sorry, let me write a Q here. It's the same in both places, but we want to calculate it in the place where we know the radius. Okay, we don't really know the radius of the bag. Okay, so V2 times pi times 0.0003 meters squared. Right? So we say that equals 3.5 times 10 to the minus 8. The whole point of this whole thing is just to get the velocity. Okay, the velocity of the solution depends on the flow rate you're trying to put in. So the velocity and the flow rate are always tied together. So if we solve that, we get that the velocity, 2, is 0.124 meters per second. Okay? So at a microscopic level, that's pretty fast. Right? This liquid is 10 centimeters a second is shooting into your vein. It's going to slow down pretty quick because it's going to bump into stuff. Right? But so now you have that V2. Okay? And then you got to decide which one of these are we going to apply, these formulas here. Are we going to apply, which approximations can we make? Well, clearly, the opening of the catheter is very small compared to the bag. I didn't even give you the size of the bag. But you can see in the picture, right? The bag is like this big. The catheter is very teeny. So we could definitely apply that approximation where we don't worry about this. We don't worry about the bottom part. We just write this. Okay? So we're going to do the sort of small leak approximation. Where did the A go? Here it is, pi r squared. There's the A. Okay, so we're going to... We're having so much fun. We'll just keep going. We will do the break. So we have a small catheter. Actually, I'm going to build up tension, and we're going to stop because I'm going to lose my voice. All right, so 5 minutes, and then we'll figure out if you get fired from your candy striper job or not. 204. All right, I know some of you can't wait to hear the answer, so we better keep going. I got one exam question. Somebody asked, is torque going to be on the exam? Well, that depends on how you handle the exam. If you pick it up like this, then there's no torque on it. But if you walk up and pick it up like this, then it does have torque. So I guess that's what you meant. Okay, so it's a slow crowd. Let's see. It's a tough room. Okay, so where were we? We're saying, oh, the catheter's small. So, so we get rid of the denominator, and we have that expression. So now are we smart enough to plug in the right numbers for that expression? Maybe. I'd give us about a 50-50. And we say V2, which isn't really what we're solving for. Well, we know V2. We'll plug it in a minute. It equals that. The square root. We might as well just put in the numbers, right? So we know V2 was 0.124. 0.124 meters per second is a square root of the difference in the pressure, right? What is the difference in the pressure? Well, the bag is at what? Oh, we got to think about the bag for a minute. What is actually happening with the bag? If you zoom in on a bag, it's like it's closed. They're sealed, and there's no air in them, mostly. So the bag is soft, is the point. So in this thing, the pressure was changing because it's a rigid container and air gets sucked out of it, right? And since it's rigid, the air lowers its pressure above it. But if it's soft, if it's a bag, then that doesn't happen. So basically the bag stays at atmospheric pressure because it has soft sides. Okay? So then we would know that it's P2 times P atmospheric minus And then the P at 0.2 is here. So is your blood at only 50 millimeters of mercury? Maybe on Mars, right? But here we also have atmospheric pressure pushing on it. Okay, so we want the absolute pressure here, not the gauge pressure. So we would say the pressure there is really this plus P atmosphere. Okay, again, if you ask the doctor, what's the pressure in a vein, and he says 50 millimeters of mercury, and you say, don't you have to add atmosphere to that? He's going to say, what? Okay, but you have to know, because you're a physicist, that, yeah, in this equation we have to add 50 mmHg minus P atmosphere. See, the point is it's just the difference, right? The two P atmospheres are going to cancel. Okay? The point is that the liquid has to go into an increase of pressure of 50 millimeters of mercury, which actually is negative in this expression because of the way we set it up. It's okay, though. Don't worry. So that whole thing divided by the density of the solution, 1020. So we got 50 in the wrong unit over 1020. That's the first part. That's 2P minus P2, or whatever it was, over rho. And then plus, in this part, is 2GH, right? So times 2 times G is 19.6. I'll just be confusing and do that. There's 2G. And there's H. What is H? Oh, we're looking for H. That was the whole, that's what you were told to do. Calculate how high you need to put the bag. Right? And then I squared both sides and here. So pretend this is a new board here, because it doesn't matter here. So you all go down. I'm going to write here. I squared both sides. I got if you want to check your numbers later, 0.0154 is the square root of minus 13 plus 12.6H. If you tell me something's wrong with that, I'm just going to tell you that you probably made a mistake. Okay? So to get to that point, I converted this to pascals, to newtons per meter squared. The quick way is to say, well, that's 50. I know an atmosphere is 760. So you say 50 over 760 times 101.325. Or you just ask Google, convert 50 millimeters of mercury to Pascal. Either one, but not during the exam. I thought it was supposed to be P minus P atmosphere. No, it was, well, okay, because in that problem, the difference of the two, it's really just the difference of the two pressures. And it depends on what they are. So in this case, we're saying P1 is P atmosphere, P2 is P atmosphere plus 50 millimeters mercury. So if you screw that up and this comes out positive, then the answer's wrong. Okay? Let's see. Is there still? Okay, let's just finish it real quick. What do you get? You get H equals 0.66 meters. Is the answer to our question. Okay. Let me answer these real fast. Where did the 0.0154 come from? That's when I squared both sides. I squared 0.124 to get that. Why is there still a square root on the right? Oh, well, there shouldn't be right now. Okay, there we go. There, you're right now. There we go. Anyway, you solve for H. And you get, that doesn't look right, does it? 12 over 16. I can't read my handwriting here. You get 0.66 meters. 0.3 over, yeah, I don't know. Finish it yourself, okay? You get a number. You get a number of meters. And yeah, I think I just have an algebraic error. 13 over, yeah, I probably had a typo. Anyway, you get a number. Is the number correct? Is your patient going to live? No, your patient's going to die. Okay, the number is too small. You get a number, I got 0.66 meters. You can see it's actually closer to a meter because 13 over 12.6, it's around a meter. Are these things really at a meter? Maybe. They're a little higher than that. It's roughly a meter. But the thing we didn't include, see that's, okay, well it's about a meter. Well, crap, okay. We didn't include viscosity. Okay, usually when you do this calculation, you have to add viscosity because there's a resistance to flow. So you need extra pressure. So the answer we got is actually a little small. It actually has to be bigger because viscosity also slows things down. We're not doing viscosity, but I'm just letting you know that if you have to make this calculation in a hospital, you know, don't forget about viscosity. Go take a better class where you learn about viscosity. Okay? That's it for fluids. Okay, we're done with fluids. Oh my God. Yay!